This is our EEE 316 project, which focuses on designing and implementing a variable lab-based DC power supply. The system utilizes of generating its own AC signal through inverter using sinusoidal pulse width modulation technique. For this, we used Wien-Bridge oscillator to generate a reference AC signal and a triangular wave generator to produce a carrier signal. These signals are compared to create PWM pulses, which drive an inverter circuit. The inverter output is rectified and subsequently regulated using the LM317 IC to produce variable DC output. At first, we generated our reference signal using a Wien-Bridge oscillator. This is our Wien-Bridge oscillator circuit. The circuit has two parts, a high-pass filter containing a 3.2 kΩ resistor and 1 microfarad capacitor in series, and a low-pass filter having a parallel 3.2 kΩ resistor and 1 microfarad capacitor connected to ground. To limit amplitude and reduce distortion, we use back-to-back diodes in the feedback loop. These diodes adjust the resistance as the amplitude increases, stabilizing the signal. In our circuit, the feedback resistors are set at 10 kΩ and 17 kΩ using a potentiometer. By adjusting the potentiometer, we set the frequency to 50 Hz and generated a 14.8 volt peak-to-peak sine wave as the reference signal. This is our carrier wave generating circuit. Now, for generating the carrier signal, we started with a square wave using Smith trigger circuit with op-amp, which stabilizes noisy signals into a square wave. Then we converted the square wave into a triangular wave using an integrated circuit with an op-amp and capacitor of 1 microfarad. A 20 kΩ potentiometer was used to adjust amplitude and a 1 kΩ potentiometer to adjust the frequency. After tuning, we produced a triangular wave with peak-to-peak voltage of 15.4 volt and a frequency of 4 kHz.
Assalamu alaikum. Till now we have seen that we have generated sine wave as reference signal and triangle wave as carrier signal. As we are implementing unipolar SPWM, we need two reference signals. So what we did is that the output of the reference signal 1 from Wien-Bridge oscillator is connected to this inverting op-amp, and it is giving the second reference signal of equal magnitude and 180 degree of phase shift. So as we are doing full bridge unipolar SPWM inverter, so we need 4 gate pulses. The first 2 gate pulses are coming from these two op-amp, and second 2 gate pulses are coming from these two op-amp. And for this, we are connecting in the first op-amp, the reference 1 signal is connected to the non-inverting terminal of the op-amp, and carrier is connected to the inverting terminal of the op-amp, and output is connected to the MOSFET gate. And similarly, for the second comparator, the reference 1 is connected to the inverting terminal of the op-amp, and carrier is connected to the non-inverting terminal of the op-amp. And now this goes to the first leg of the MOSFET, and for the second leg of the inverter, we have used these two comparator circuit where reference 2 and carrier signal are used in the similar fashion explained as before. So in SPWM inverter, if we need undistorted output, the modulation index should be less than 1. So we have chosen the value or we have set the value of reference signal and carrier signal in such a way that the modulation index is less than 1. So we in our project we set sine reference signal amplitude was around 14.8 volt, and the amplitude of carrier signal was around 15.5 volt. So if we calculate the modulation index, which is the peak of the reference signal divided by peak of the carrier signal, is less than 1. And so to wrap it up, till now we have generated 4 pulses. Among them, the pulses of each leg are complementary to each other. Thank you.
Now I will explain how the bridge inverter generates the output and how the RLC filter processes it to produce a clean sine wave. We are giving gate pulses in our MOSFETs from the output of our comparator circuits, and we have connected freewheeling diode across the drain and source of each MOSFET. So as you can see here, our circuit consists of 4 MOSFET switches, Q1, Q2, Q3 and Q4. These switches operate in 2 modes. In mode 1, Q1 and Q4 are turned on while Q2 and Q3 are turned off. It produces a positive voltage across the load. In mode 2, Q2 and Q3 are turned on while Q1 and Q4 are turned off. It produces a negative voltage across the load. Here, the output from our inverter circuit will be pre-filtered output. For getting a pure sine wave, we are using an RLC filter here. An RLC filter smooths the output waveform of the inverter, and our RLC filter consists of 2 inductors in series and 1 capacitor and 1 resistor in parallel. The inductor resists changes in current, suppressing high frequency components. The capacitor blocks DC components and smooths voltage by storing and releasing energy. Together, they work to remove high frequency noise and harmonics, leaving us with a clean sinusoidal waveform at the output.
The last 2 parts of our project includes rectification and voltage regulation. The AC output from the full bridge inverter is passed through a full bridge rectifier as shown in this 4-diode circuit configuration. This output is then fed into an LM317 voltage regulator circuit. For this part, we had initially planned to implement a SEPIC converter. However, due to the unavailability of inductors and low current flow from the previous parts of the circuit, we couldn't go through this plan. We could implement a SEPIC converter separately, however, integration was not successful. So we opted for a more versatile and robust LM317 circuit, which is a variable voltage regulator. This IC has 3 pins, input, adjustment, and output in the order mentioned. The capacitors added are used for ripple rejection so that it cancels out the amplification of ripple voltage at higher voltages. We also added diodes in these places to provide alternative discharge paths. LM317 is essentially a voltage divider which uses these 3 resistors to produce variable output voltage. These 100, 200 ohm resistors and 5K pot is used in series, and turning this pot will allow us to change the voltage. Now this will be explained further and demonstrated by my lab mate Mushfiq.
This is our voltage regulation circuit. We can see the rectified output from the sine wave is almost 7.75 to 76 volt. Now we can see the output of the voltage regulator as the output is almost 5 volt at the peak range and 0 volt at the minimum. Now let us see how the voltage is regulated. Please my lab mate change the voltage regulator pot. As you can see, as she is decreasing, the voltage is regulated from 5 volt to almost 0 volt, and like you can see,